Hello once again, everybody. I'm meteorologist Sean Sublette, and welcome to Across the Sky, our national Lee Enterprises weather podcast. Lee Enterprises has print and digital news operations in 77 locations across the country, including in my home base in Richmond, Virginia. I'm joined by my meteorologist colleagues from across the sky, Matt Holiner in Chicago and Joe Martucci at the New Jersey Shore. Our colleague Kirsten is taking some well-deserved time off in Tulsa for a couple of weeks. And guys, we've got Daniel West on the podcast today. A lot of people know him as Weather West. Why are you shaking your head at me?
Daniel Swain.
Okay, Daniel Swain. Daniel Swain. He's Weather West.
Yes.
Y'all knew where I was going with this.
Yeah, of course, without a doubt.
Man. And he's great. I mean, I've done some work with him when I was with Climate Central. He's just got a wonderful, wonderful grip on what the weather and the climate are in the western part of the country. And it's really, really nice.
Yeah, well, Sean, it's a good follow-up from last week's episode where we talked with Donnie down at the Placer County Department of Public Works about all the snow that they plowed. So we have the boots on the ground with your last episode with Donnie. This time we're taking it from the academic perspective and the forecasting and the look back perspective with Daniel Swain. So it's a good 1-2 punch as we really exit out of the cool season. And then we promise we'll talk about warmer and more summery things as we go forward over the next couple of episodes.
Yeah, this was a real interesting conversation with Daniel because he's just, really focused in on the West. And I think oftentimes, us meteorologists in the central and eastern part of the country, because it seems like a lot of the time there's not much going on in the West, so it doesn't get discussed much. But boy, this winter was truly the exception. There was lots of talk on the national level about what's going on out West. And, it kind of like shifted attention. It's like, wait a minute, I thought that, nothing happened in the West. It's just constant, never ending drought and wildfires. Well, this year was the proof that you can't forget about what's going on out West, because it's not going to be drought all the time. It's not going to just be wildfires all the time. They're still going to get big rains. They're still going to get big snows. And look at the impacts that it caused. And of course, Daniel is tuned in with the West all the time and is aware that it's not just drought going on out there. So he was the perfect person to bring on and really dive into this. This was a fascinating discussion.
Yeah, it really was. So we were glad to have him. So let's cue it all up and get our discussion started with Daniel Swain there at UCLA. And our guest this week is Daniel Swain, climate scientist at the Institute of Environment and Sustainability at UCLA and author of the popular Weather West blog and YouTube channel. He has been featured on numerous digital and legacy broadcast outlets talking about weather and climate in the Western U.S., and we are absolutely delighted to have Daniel on the podcast. It has been so busy, I know, for you, Daniel. Thank you so much for joining us on the Across the Sky podcast.
Thanks again for having me. Glad to be here.
I do want to talk about some of the big picture items down the road, but first let's talk about immediacy. These next, let's say 1 to 3 weeks there in California. Of course, we had the phenomenal amount of snow. Everybody kind of gets that, but now it's starting to melt, and we've got kind of a hot spell actually developing. So what does this kind of portend or kind of lay the groundwork with regarding flooding there in California in the coming, let's say, 1, 2, or 3 weeks?
Well, I think you've nailed most of the key points there, but I think it's worth digging into a couple of them because, California, just to review, had an exceptionally wet winter in the central part of the state, which includes the southern half of the Sierra Nevada mountain range. And really phenomenal amount of snow accumulated, tens of feet at the higher elevations in these places. And so currently the water stored in that snowpack in the southern Sierra is on the order of 2 to 3 times the average amount. So 200 to 300% of average, which in some places in the far southern Sierra is the largest amount ever observed at this point in the season. So there is a huge amount of water up there, the vast majority of which is still yet to melt. And all of that melt is eventually going to end up in rivers and streams that drain mainly down the western slopes of the mountain range into California's Central Valley and the San Joaquin Valley and Tulare Lake basins in particular. So all of that water that's up there in the mountains right now as snowpack is eventually going to make its way to lower elevation areas. And probably, given this heat wave that's going to ramp up later this week, a lot of that's going to melt sooner rather than later.
Can I get you to talk a little bit about Tulare Lake? I've just become aware of this over the last 3 or 4 weeks. I did not know that there was an actual lake there decades and decades ago, but there has been a change. So what is that all about there, and about what part of California is that?
Yeah, Tulare Lake is, or was, I guess, was and perhaps will be, maybe is the best way of putting it, given what's going on right now, the largest freshwater lake west of the Mississippi. This was quite a substantial body of water in the southern San Joaquin Valley of California. It was indeed a century or so ago drained, mainly so it could be used for agricultural purposes, but also a number of people now live within this historic lake bed, which is sort of maintaining itself in most years from becoming a lake again by having lots of levees and dikes and conduits, artificial interventions to keep the water away, essentially. And in recent years, recent drought years, flood risk has been far afield. People haven't really been thinking about it, but now that we've gotten a very wet winter in this part of the state, now that we have this enormous snowpack upstream, a lot of that water is accumulating in this basin, and there is no outlet to the ocean in Tulare Lake Basin unless the flooding gets very severe and it spills over the top of the basin into the San Joaquin River. The water that flows into Tulare Lake Basin, it stays there, it accumulates. And so we're hearing about all this flooding. That water isn't going to by itself just gradually drain out to the ocean. That water is just going to sit there and continue to get deeper as more and more water flows in. So one challenge, in addition to all the water that's flowing in from snowmelt and rain this past winter, is that the ground itself has subsided, literally sunk, in the Tulare Lake Basin in recent years due to groundwater pumping during severe drought. So we're actually seeing probably flooding that will be deeper and more prolonged here in this wet spell because of the drought conditions that just ended, and the human response to that drought being to pump all this water out of the aquifers. The ground has sunk in some places by 10 or more feet. So this is not a barely measurable thing. This is, I'm 6'4", and the ground has sunk by, considerably more than my height in recent years. That's going to affect the flooding in ways that are, I think, hard to predict from the outset.
Yeah, before I turn this over to Joe, I know you want to go next, but can you give us a little more idea of how big this lake is, let's say, compared to someplace like the Great Salt Lake? Is it about that size, half of that, larger, just for some kind of frame of reference?
Well, I don't have the numbers off the top of my head, but it's the challenge is this, especially this type of lake, doesn't have a fixed size. During the Great Flood of 1862, for example, much of the Central Valley, all the way from the southern San Joaquin up to the northern Sacramento, I mean, that's 250, 300-mile stretch. It was contiguously inundated. It actually become one giant freshwater lake, almost 300 miles long, encompassing areas that are now home to millions of people and most of California's agriculture industry. So, if you measured it then, it would have been, a truly enormous body of water. If you measured it last year, there's zero. It didn't exist. So it's, we often think about bodies of water as these dynamic, fixed things, and that's almost never the case. But it's especially wasn't true even in its natural state for Tulare Lake. This was something that waxed and waned greatly from year to year before human intervention. It has done so less since we drained it. But in the big years, it's going to come back. And this year, Tulare Lake is making a big time reappearance.
Hey, Daniel, it's Joe here. I want to take a step back and get into your initial interest in weather here and maybe extreme weather. I know you went to, I believe, UC Davis for your bachelor's and then got a PhD from Stanford. What drove you to be interested in weather and in getting into the subset of the field that you're in now?
Well, I was always a bit of a weather geek, maybe more than a bit of a weather geek, if I'm being totally honest. So actually, my undergraduate degree is in atmospheric science. So I actually specifically wanted to pursue, be in a degree program that would give you the credentials to become an operational meteorologist, day-to-day weather forecasting. And so I do have that degree, but then at some point in this process, I realized, I'm still really interested in weather, but the big societal and scientific problems that are really interesting these days really seem to be sort of at this weather climate nexus. So I'm really fascinated by the day-to-day variations in weather. I enjoy cloud watching and watching storms and things like that. But also, and that's where the societal impacts come from, right? Like climate change is affecting all of us. It's affecting ecosystems everywhere. But exactly how is it doing so? Usually it's doing so by changing the envelope of extreme weather events, shifting the range of what's possible or what's likely from what it used to be. And so it turns out that this is kind of a niche that's underdeveloped, or it certainly had been for decades, where weather scientists, meteorologists, and climate scientists were kind of siloed from each other. They're kind of viewed as different disciplines, which always struck me as a little bit odd because it's the same atmosphere and it's the same physics and chemistry. It's just different timescales. And so, yes, you often use different assumptions, but I think that separation has perhaps been too strict and too rigid. So I live a little dangerously and I mix my weather and my climate. They are different things, of course, but what is climate but the weather in aggregate? That's something I often like to say, because it's not just the average of weather, but it's also the extremes of weather. It's the swings in weather, it's the variability too. So for me, that's sort of that weather climate nexus is what really, I think, fascinates me. And now that I'm a climate scientist who has a background in meteorology and really thinks about climate change from a weather up perspective, if you will.
Hey, Daniel, it's Matt. And going off of that, I kind of want to take a step back and look at the bigger picture, because there's been a lot of buzz lately, of course, about all these atmospheric river events and the improvement in the drought situation, even the removal of drought, particularly in California. But when you look at the big picture, I think what's getting lost a little bit is people think that the West is now completely drought-free, and that's definitely not the case. In fact, in some parts of the West, there's still some extreme drought, not in California anymore, but other parts of the West. And so what can you say about, the longer-term trend? Yes, we had this really wet winter, and there was improvement in drought across the West, but is this going to continue? Are we going to go back to drought? What can you say about the general Western U.S. in general and the outlook for drought there?
I think this is an important point because this has been, of course, a good water year in California, and actually across much of the lower Colorado Basin, which is the area in crisis because of the very low levels of flow on the Colorado River and all the big dams. You hear about Lake Powell, Lake Mead, and the sort of the growing crisis there with water scarcity. This, of course, helps in the short term in these places where, there's been a good snowpack in the lower Colorado Basin. There'll be better inflows into these reservoirs this spring and summer than there have been in recent years, that's for sure. But it certainly, as you say, doesn't solve the long-term problem, because this really took decades on the Colorado Basin to develop. So one good year certainly doesn't erase decades of accumulated water scarcity. And in California, I think the situation is a bit different because a lot of California gets its water from more local watersheds. So the northern 2/3 of the state sees water mainly as in the form of local reservoirs, and then also snowmelt from the Sierra Nevada. And here, the drought, I think is fair to say, has broken. But there's this broader question of what drought means in a warming climate, I think, which is really actually quite an active topic of research and conversation, because it's not entirely obvious. And a lot of what's happened in the West isn't so much because of lack of rain or precipitation, but it's more just that temperatures have been so much warmer in recent decades than they were in the 20th century, that the evaporative demand, literally the thirstiness of the atmosphere, its propensity to act as a giant sponge and extract water out of the landscape, has increased. This is known as the increasing vapor pressure deficit in technical terms. And what it does is it just extracts more and more water out of the landscape more quickly. And unless you're seeing more precipitation than you used to on average, which we're not, then there's going to be an accumulated deficit over time. So it's not just a question of the low precipitation years, but it's also a question of the high evaporative demand years, which increasingly have been almost every year, both the wet precipitation years and the dry precipitation years. So what does it mean in a warming climate to have individual episodic wet periods? Do they completely counterbalance the accumulated increased atmospheric sponginess, if you will, all the rest of the time? The math really doesn't pencil out, because you'd need to get a lot of extra precipitation for that to be true. And we're not seeing a lot of extra precipitation. Now, in California in particular, and this is probably true to somewhat lesser extent in most of the West, we don't just expect to see drying in the future. In fact, in California, the hydroclimate signature of climate change really appears to be increased variability. We call it increased precipitation or hydroclimate whiplash because of how it kind of feels like to just wildly swing from dry to wet and back and forth. And this again comes from that basic thermodynamics of the atmosphere. That increased atmospheric sponginess I mentioned goes both ways. It both increases the atmosphere's ability to extract water out of the landscape. Think a larger and larger dry sponge soaking more and more water up off your counter when you spill a glass of water or something. But on the other hand, that progressively larger sponge, once you've soaked up that water, you can wring out more water too in the form of more intense precipitation. So in California, the signature really seems to be more of both, more of the very dry conditions on the one hand, and more of the very wet conditions on the other. And I think this is largely going to be true across much of the Southwest. So in the long run, of course, if you only take the average, that might pencil out to be similar. But in practical terms, does it actually feel similar? No, not at all. This is a radically different regime, with either you're very wet or you're very dry increasingly, but you're really rarely in the middle. And I think we've seen that a lot this decade, where parts of California in particular have seen both record dry conditions and record wet conditions, in some cases more than once in the past decade, where we've broken century-long precipitation records and then also broken century-long non-precipitation or dryness records in the same decade in the same place.
On to that point about getting so much precipitation at once, there's also been a lot of discussion about groundwater, especially in California and in the Central Valley in particular, since so much of the wintertime vegetables certainly are grown there. When we have a situation like we had this past winter, how much does that help with groundwater? I mean, obviously we're still very dry in the longer term, but would you say that this also helps the groundwater situation, or at least buys us a little time?
Well, this is a pretty complicated question, and I'm neither a geologist nor a hydrologist, but the situation is complicated mainly because it's not just a question of pouring a bunch of water on the ground and hoping that it soaks in. Unfortunately, we've done long-term damage to the aquifers themselves by so much pumping. In fact, when I was talking about subsidence earlier, literally the ground sinking, the reason why it's sinking is all of that pore space. In other words, essentially the air bubbles, not really bubbles, but the spaces in between soil particles and in between rocks has become compressed over time. And so that compression, you've lost the space where the water would have gone. Aquifers generally, some folks think of them as these huge open caverns where water, sits. That's really not what they are. They're actually, it's just the accumulated effect, and that effect of huge amounts of small air pockets that can fill up with water if the soil gets saturated. If you compress those air pockets enough, they don't magically reappear when you dump water on top of the ground. Now the water just kind of likes to sit there on the top of the ground and cause flooding and then run off into rivers and into the ocean eventually, rather than soaking in nicely. So unfortunately, there's some long-term damage we've done to aquifers in some places that makes it harder for them to recharge when we do get wet years like this. And the other reality is that in general, even in an ideal undisturbed water system, there are only some places where aquifer recharge happens at a good pace. There are some places where naturally the soil is just too full of clay or rock to really allow rapid recharge. You need to have water sitting there for years, not just for one season. And so for these reasons, I think that the groundwater problem is not remotely going to be solved by even one, probably not even by two consecutive very wet winters. It certainly helps, but it mainly helps because what it means is that there's less desire to pump water out of the ground. So it helps mainly in an indirect way because it means that there are fewer straws sucking that water out of the aquifer because there's water available elsewhere. There is some recharge going on. There is movement to actively facilitate that recharge as a groundwater management and flood control strategy in California, which I'm optimistic about moving forward. But it's tricky because just because there's a lot of water doesn't magically mean that you've recharged aquifers. And, this is going to be an ongoing problem, unfortunately. So no, that part of the long-term scarcity problem is definitely not solved by one really good year like this one.
And it also underscores the need for cross-disciplinary work between the geologists, the hydrologists, and meteorologists and climate scientists. We're going to take a little bit of a break, then we'll come right back with Daniel Swain and talk about El Nino, talk about some atmospheric rivers when we come back on the Across the Sky podcast. And we're back with Daniel Swain, Weather West, on the Across the Sky podcast, talking about the very wild winter and the repercussions for that in the Western United States. So Daniel, we just came off the third consecutive La Nina, which oftentimes means it's drier than average. And all signs are pointing toward going into an El Nino into this late this summer, into perhaps this coming winter, which oftentimes means wetter than average. Not always, but oftentimes. How do you kind of reconcile those things? I mean, we know that it's not one-to-one, but how do you kind of reconcile those things to the public?
Yeah, this has become actually a really major and consequential weather and climate science communication challenge in California, because it's probably helpful to think a little bit to review the history actually of El Nino in California in pop culture first, because really the first El Nino event of prominent public dialogue was back in the early 80s. So this was the 1982-83 event, which was an exceptionally wet year in California. There was a lot of flooding and there were a lot of problems, and folks in the media really linked that event to the very wet conditions that occurred at that point, and with good scientific reason. The scientists agreed. Then there was another big El Nino event in 97-98 of similar magnitude, which was again a very wet winter in California with lots of flood-related impacts. And so that really reinforced this public idea that major El Nino events were wet years in California. Then in 2015, 2016, there was another strong El Nino event, and everyone got excited about how it was going to break the drought, and then it didn't. It was not an exceptionally wet winter, and California did not experience, significant drought relief as a result that year. Now, we're heading into another year where, indeed, as you say, it does look quite likely. I would say probably 80-90% chance at this point that an El Nino of some magnitude will emerge later this year. But interestingly, the public dialogue is now centered, including in the local media, around how El Nino is so uncertain that it doesn't matter. And I think we've swung too far back in that direction. It is absolutely true that El Nino is not everything, and that there are other influences that in some years can completely override its influence and produce an opposite outcome even. But on the other hand, there are a lot of pretty basic physical science reasons why especially strong El Ninos in particular really should and do influence the hydroclimate of the American Southwest pretty profoundly. And no, as you say, it's not a perfect relationship, but I think the challenge is a lot of folks go and try and do a literal linear correlation between the El Nino ocean surface temperatures anomalies and average annual precipitation. And of course, that signal is pretty weak in a lot of places. But if you focus only on the strong events and you focus specifically on El Nino, which is a bit asymmetric from its counterpart La Nina, we'll talk about that a bit in a minute, but there still is a pretty strong signal. So yes, if El Nino is strong, despite the failure in 15-16, I would still put my money on a wetter than average winter, perhaps a greatly wetter than average winter, especially in central and southern California and in some parts of the lower Colorado basin. So there's usually a dividing line in El Nino and La Nina years, separating the Pacific Northwest from the rest of the West, and usually it's the opposite sign. So when the Pacific Northwest is dry, the rest of the West is often wet, and vice versa. And usually in El Nino, the wet conditions occur in California and the Southwest, and then the Pacific Northwest is dry, and in La Nina, the opposite is true, where La Nina is wet in the Pacific Northwest and dry in the Pacific Southwest. Of course, that's subject to some variability, but I think that's a pattern that in the long run still holds true for reasons that physically makes sense. But let's back up for a moment and think, okay, so what is El Nino and La Nina? What is this in the first place? Well, technically, it doesn't directly have anything to do with the Western United States. It's a tropical ocean temperature oscillation that is strongly coupled with the tropical atmosphere. So El Nino simply means that ocean surface temperatures in the eastern part of the tropical Pacific Ocean have been warmer than average for a sufficiently long period. And La Nina simply means that ocean surface temperatures in the eastern tropical Pacific have been cooler than average for a sufficiently long period. So there need not necessarily be any specific conditions in California or the American West for an El Nino or a La Nina to occur. And it's worth noting that even in 2015, 2016, where the rains did not come in great volume to California, the prediction for a strong El Nino event was correct. The strong El Nino event occurred in the tropical Pacific Ocean. It's just that it didn't produce the results that some folks had anticipated. And, there's been lots of research on why that is. It's probably a bit in the weeds for this conversation, but I think in the long run, I would still put my money on particularly for a strong El Nino event. And it looks like there's a decent chance that's where we're headed this year. Although it's still a little bit early to talk the intensity, that we might end up seeing back-to-back unusually wet winters in California and parts of the lower Colorado, which we have not seen in quite some time.
Yeah, you got me thinking back to now, this recent winter that we had here. What were predictions for snow and precipitation and atmospheric river events going into this past winter? And then I believe, and I saw some reports of there were 31 atmospheric river events, or these atmospheric river is a relatively narrow but intense moisture plume that comes in. But where were the forecasts versus reality going into this winter?
Yeah, and I will emphasize that there were more like 15 or 16 atmospheric rivers in California. I think the 31 numbers for all of the West Coast. But that's still a very high number for California.
Yeah, my fault on that one. Sorry.
No worries. Well, so the seasonal prediction for California this past season was, as has been the topic of discussion, was for a slight tilt in the odds towards drier than average conditions because of the moderate to almost strong and a persistent third-year persistence of La Nina. Now, obviously, that didn't happen. But if you look at the large-scale atmospheric pattern, though, it's kind of interesting. So the reason why there's a slight tilt in the odds towards drier than average conditions during a significant La Nina event is because it tends to favor a strong ridge of high pressure somewhere over the Gulf of Alaska. As it turned out, that did actually happen. There was a seasonally persistent ridge in the Gulf of Alaska. But the problem, or maybe the saving grace for California, was that it was slightly farther to the west than the typical position of the La Nina ridge. And so instead of blocking storms from making it to California and dropping rainfall and snowfall, it actually was far enough to the west that the return southward flow on the eastern flank of that high pressure system injected a bunch of cold air and atmospheric instability into the mix and helped juice up these subtropical moisture plumes, producing a bunch of atmospheric river storms and a persistent stream of significant storminess all winter long. So physically, the high pressure system that's connected with cool temperatures in the eastern tropical Pacific essentially happened, but something else occurred that shifted it a little farther west than had been initially anticipated, and that resulted in an enormous difference for California, an exceptionally wet winter in some places instead of a drier than average winter. This was something I actually talked about in a blog post back in the autumn last year, which is that, the problem with La Nina and the reason why this linear correlation is not so great is because if you tried to linear correlate La Nina with the ridge in the Gulf of Alaska, that'd be a very strong correlation. But the problem is the relationship between that ridge and California precipitation is very tenuous. We're kind of on the razor's edge. If it's far enough to the east, we are warm and dry in the winter. But if it's far enough west, it's literally the opposite surface conditions. It's cold and wet because of the direction that the winds end up coming from. So that's the hard part, is getting the exact longitude of that big ridge correct months in advance. So you can't just say there'll be a big red blob somewhere in the Gulf of Alaska. You need to be able to say exactly where it is, because if you're off by even 500 or 800 miles, which is not a very big margin on the global planetary climate seasonal prediction scale, you get the completely wrong outcome for California. And I think that's what happened this year, where that ridge was just too far west, and we were on the other side of that razor's edge in California on the cool and wet side this year.
Yeah, as is true with much of meteorology, little differences add up and can lead to some big changes in the ultimate outcome. One thing I want to look ahead to, what has been, again, until this winter and all the snow and the atmospheric river vents, besides the drought in the West, the other thing that got a lot of attention in the West was wildfire season, how these wildfire seasons seem to keep getting worse with very little fluctuation. So I kind of want to look ahead to this wildfire season as we get through the summer and things quiet down and get into the fall. What are you thinking as far as wildfires go in the West this year?
It's a complicated picture this year because there's, as you mentioned earlier, there are actually patches of drought that have gotten worse this winter. Despite the rapid improvement in the California and the Colorado Basin, the Pacific Northwest, for example, is headed for a significant drought right now. So we might actually see a relatively worse fire season in the Pacific Northwest later this year than in some other places. The other thing is that even within California, for example, there's great complexity. So we have such a large snowpack that I think the high elevation fire season this year in California and throughout most of the West, fortunately, will be pretty mild because literally there is snow on the ground. It's impossible to have wildfires of any real magnitude right now. And that might still be the case for a few more months. So by the time August gets around, the snowpack is finally melting away. Well, you don't have snow on the ground anymore, but now you have all this residual soil moisture. So everything is going to be pretty damp up at high elevations. I don't think we're going to see, and this has been a really big problem in recent years. We have seen very high elevation, high intensity wildfires, which were historically rare and have recently become much more common. I don't think we'll see that this year in places that have a really exceptional snowpack. So that's some good news, a place where I think there will be a mitigated fire season up above 7,000, 8,000, 9,000 feet. Of course, there's a lot of territory in the West. In fact, the vast majority of the West is below that elevation. So what happens there? Well, it depends a bit on the ecosystem type. It's actually the case in a lot of the West that the wet years tend to be worse fire years historically, because what it means is you have a lot of extra growth of brush and grass. So if you're in the desert, if you're in grasslands or even sort of mixed trees and brush and grass woodland kind of regimes, you usually get worse fire years after wet winters because you have so much more fuel to burn. That's because these are regimes that are actually known as fuel limited, meaning that the reason why you don't have more widespread and more intense fires is usually because there isn't enough vegetation to burn on average. Well, these are the years where there is enough vegetation to burn because you've grown extra because there's so much more water than usual. So all of that greenery you're seeing now, lower elevations, it will become eventually fuel for fires later in the season. And so there's also this interesting dynamic where in places like California, where there were severe windstorms and snowstorms in these middle elevation zones this winter, there's a lot of trees and branches that came down, which are going to end up essentially forming additional fuel for fires later this season as well, along with all that extra brush and grass growth. So this could be a year where if we do get significant wind or heat or events at the end of the season, we could see a pretty serious fire year in certain lower elevation zones, but a really mild fire year at higher elevations. And so I think there's both geographic variation where the Pacific Northwest is actually pretty dry right now, but the Pacific Southwest is pretty wet. And there's also elevational dependence where places that had a big snowpack right now probably aren't going to have much of a fire season this year, but the lower elevations might see potentially a elevated fire season in some places, depending on how things go.
Yeah, that's really the irony of the whole bit, to be sure. Before we let you go, I do want to talk a little bit more about atmospheric rivers. I think that term has really jumped into the lexicon over the last 5 to 10 years, especially in the West. What do we know about atmospheric rivers and the warming climate in general?
Yeah, so there's a strong consensus at this point in the scientific literature that the strongest atmospheric rivers will become considerably stronger moisture and produce more intense precipitation in a warming climate. Interestingly, there's less consensus about what happens on average to the frequency of atmospheric rivers overall. So really the strongest argument that we can say is that really throughout Western North America, where atmospheric rivers are relevant, that the most extreme atmospheric rivers in a warming climate will be significantly wetter and will pose significantly greater flood risks. That doesn't necessarily mean we're going to see more atmospheric rivers overall. In fact, we may even see in some places like California more variability of atmospheric rivers from year to year, where the wet years are really wet, increasingly so. And as I mentioned earlier, the dry years are perhaps even drier. This really comes down once again to basic thermodynamics. As you mentioned, atmospheric rivers are at their core these concentrated plumes of atmospheric water vapor, long but narrow, pushed by strong winds over your head. They can carry volumes of water that are many times that of the Mississippi River in flood, but in the form of vapor over your head. So these are huge amounts of water volume that we're talking about. And you can imagine that in a warming climate where the water vapor holding capacity of the atmosphere increases exponentially for each linear increment of warming. So in other words, this is about 7% per centigrade, degree centigrade, or about 4% per degree Fahrenheit of warming. That atmospheric sponginess increases by either 4% per Fahrenheit or 7% per degree Celsius. That would be a pretty darn good compound interest rate in a bank if you get a 4 or 7% guaranteed return. I think anybody would be excited about that, but it's a little bit scary when we talk about it in the context of the ceiling on extreme precipitation, which by our best estimates does increase by about 4 to 7% per Fahrenheit or Celsius degree of warming. And globally, we're already at, 1.2 or so degrees Celsius of warming, getting close to 2 degrees Fahrenheit of warming. Locally in California, during, in some places, we're already higher than that because, the land is warming faster than the ocean. So this is not an insignificant change.
Yeah, for sure. And I think that's one of the things that I think all of us as scientists and it's meteorology or climate science, I think a lot of people understand outside of the scientific disciplines that, yeah, if it's warmer, you can evaporate more. I think a lot of that's intuitive, but I'm with you. I don't think people understand that it's not linear. It goes up dramatically as you get warmer, so that when we do have these higher end events, they are so much worse. Daniel, we're going to cut you loose. We appreciate you joining us. In addition to the Twitter and YouTube, where else can people find out about the work you do?
Well, I do also write the Weather West blog. You can find that at weatherwest.com. As you mentioned, I try and spread my public-facing science communication across these platforms, Twitter, YouTube, and my own weatherwest.com. So, and, I like to join other people's podcasts on a pretty regular basis too. So you can find me here, there, and everywhere, I guess.
Daniel, terrific. Thanks again so much. I know you're busy. It has been a wild winter and early spring and now mid-spring there in the Western United States. So we hope to talk to you again real soon. Thank you so much for joining us.
Thanks again for having me.
I will be right back with a few closing thoughts on the Across the Sky podcast. And we're back with some closing thoughts on the Across the Sky podcast. I'm meteorologist Sean Sublette at the Richmond Times-Dispatch, along with Matt Holiner in Chicago and Joe Martucci at the Jersey Shore at the Press of Atlantic City. And Daniel, guys, he has such a deep understanding of the weather patterns there. We kind of forget about how volatile it can be in the Western United States. We've all kind of, got locked into this idea, well, it's dry and it rains on occasion and they're in trouble. They're running out of water. And then you have a winter like they just had there in the Western United States. And it really reminds you just how volatile can be. They don't have tornadoes and hurricanes like we have east of the Rockies, but they have their own entire set of issues. That is for sure.
Yeah. And he did explain all the intricacies of water and making sure there's enough water for everybody. I mean, the one thing that stuck out was how much some of that land has been sinking in the valley just through pumping out the aquifers. I think I've even seen a couple of photos online of like these huge rulers. Have you guys ever seen these? Like these huge rulers of like tens of feet about how much actually the land has sunk over the past couple of decades. So, and the other thing is too, one of these really wet winters is good. Still a long way to go to being really on top of it there. And when you throw in the climate change factor, and I like to say this a lot of time to people too, it's not so much as just, we're warm. We're more variable in our weather events. And when it comes to Western water management, that's something that is just getting, I believe, harder for our water managers to take into control in terms of these forecasts, because we do have, hey, we had an extremely wet winter this past winter. And as Daniel said, he's trending towards having another one of these kind of winters as we go into next winter. Good news in the short term. We have to see what it means in the long term.
Well, the other thing that stands out to me is just how the atmosphere is becoming more extreme. We were dealing with the extreme drought, and then quickly switched, and remarkably how quickly we switched to extreme rain and flooding. And that's just what we're seeing with climate change, is how the extreme nature of these events, these extreme events, are happening more frequently. I mean, you can talk about, and it goes with other areas too, when you're looking at, the intensity of hurricanes, for example, there's some uncertainty in the exact number of hurricanes and how that's going to change with climate change. But what there is a clear trend towards is an increase in intense hurricanes, and an increase, as Daniel referred to, it's still uncertain exactly the number of atmospheric rivers that we're going to see. But when there is an atmospheric river, it's more likely to be an extreme atmospheric river. When we have a drought, it's more likely to be an extreme drought. So there's going to be fluctuations. It doesn't mean like the West is always going to have droughts or it's always going to be in flood. It's more complex than that. But what we are clearly seeing is a trend in these more extreme events, which is the most high impact from an economic standpoint, and the toll that it takes on people. So, gosh, that's what really stands out to me, is just how many extreme events, and not just in the West, but across the planet.
Yeah, I mean, we've always known that part of the United States has very highly variable weather to begin with, and they're kind of susceptible to dry and then wet periods. But I think that Daniel's point is that we're really seeing that ratcheted up even further. And, we try to remind people it doesn't all just balance out, because the evaporation rates are so much higher in a warming climate, so that the ground dries out faster. And if you have heavy rain on dry ground, there's more running off than it would be if the ground was a little bit moist. Kind of like, you turn the spigot on top of a wet sponge versus a dry sponge. You get two very, very different impacts from that. So it is going to be quite a challenge for water management, certainly in the Western United States, for decades and decades to come. With that, we're going to close it up for this week. We do have a few more things kind of percolating in the weeks to come. We've had the Aurora Borealis show up, so we're kind of working on a couple of things there. We hope to have some news on that coming up soon. But for right now, for Matt Holiner in Chicago, Joe Martucci in Atlantic City, and Kirsten Lang in Tulsa, I'm meteorologist Sean Sublette, and we will see you next time on the Across the Sky podcast.